MindWare Technologies, and I'm going to be walking you through our second webinar of our 2026 series. So, some initial reminders here. We are going to be presenting this webinar via Zoom, and you'll have your video and audio turned off for the duration of the webinar. If you are having any issues with audio or hearing, please feel free to send a quick message into our chat. We have our research support team on standby who can help you with troubleshooting if you're having any audio issues. So that being said, in addition to troubleshooting, please at any time as we work through this presentation, feel free to send any questions into the Zoom chat. Our scientific support team will be able to go through and answer your questions. And from there, we will also spend time talking about these questions at our Q&A portion, the last half hour of our webinar. So one thing I wanted to highlight is a few of our services that are maybe a bit lesser known. So in addition to our hardware and software solutions that we offer, we also offer laboratory design services. So traditionally, you would think of this of if you got your startup, you're looking to build out your lab, and you want to have integrated multimodal systems that are completely synchronized. We can design it for you, come out and implement it, and make sure everything is configured correctly. The other thing to note here too is, say you're interested in expanding your MindWare lab and you're introducing other physiological approaches or devices, but you don't know how to get them all to talk to one another. So even if you are purchasing new equipment that doesn't have any physiological components necessarily from MindWare, we can still help you go and design and make sure that everything integrates as you planned. So dual laboratory design services here. Additionally, I wanted to break this down as far as talking through the hardware and software solutions when we are thinking of a traditional MindWare lab that has multimodal components between physiology, audio, video, and other things maybe like eye tracking. So when we are thinking of our analysis pipeline and data collection, everything will start in BioLab. And with BioLab, we will use this as the control center of where we will be able to synchronize your physio with your cameras, as well as any other systems that you're using. And following this acquisition, you will be able to go through and it's recommended that you would analyze your behavioral data of your videos within a software potentially like Mangles Interact, and analyze all of your data there first. Same thing would go for if you were looking at something like eye tracking data, you would want to do all of this analysis in Toby's Pro Lab software first. Once these are completed, you can then take these event markers and areas of interest as far as behaviors or what people were looking at and use them as event markers in your physiological data so that we can start to look at more behaviorally driven physiological analyses. So really whole picture here. And one thing that I'm very, very excited to talk about today is the rollout of our online platform, Thinkific, where we are going to be creating a series of online courses of common topics that people do training on to live as an online resource for you all. So the first course that we're rolling out is our mobile setup. This is a completely free course, so feel free to scan the QR code if you are interested in registering for it. With Thinkific, what this will do is this is an online course that will walk you through the start and finish of inventorying your order to configuring your mobile and getting it connected into BioLab, as well as all troubleshooting and permission issues that you may tackle along the way. This is a really great resource, especially if you have new students, new research assistants coming up in the fall who need to get familiar with working with the mobile device and how to connect it into BioLab. This is a one-stop shop that can save you some time and also have them review these online resources as a reference for later on too. Additionally, this is the first course that we are rolling out, but there will be announcements of more courses in the future as it relates to things like data privacy and all of our analysis applications as well. Okay, before we dive into the content of pulse wave velocity today, I wanted to give a special thanks to Mark Scudder and Pete Gennaros. A lot of what we will be referencing today is going to be work that's come out of their research lab. So in the making of this webinar, they were incredibly helpful as far as providing insights of how to take pulse wave velocity and make it very replicable for people who have never done it before, and also through this very holistic approach to research. So you'll see a lot of their citations today, a lot of their references, and they've also provided some very gorgeous data samples that we'll be looking at later as well. Okay. So let's dive in by just talking about a brief intro of pulse wave velocity. So pulse wave velocity is a measure of how quickly the arterial pulse travels through the vasculature. And historically, measuring it has required specialized vascular equipment. This has been a much more medically leaning measure for a long time, but advances in less invasive acquisition methods have made it much more practical for research laboratories. So the reason that I wanted to highlight pulse wave velocity for this webinar is because this really is a measure that's maybe hidden in plain sight for you. Depending on your current hardware, if you're someone who works with dyads, you already may have two mobiles that are frequency offset from one another so that we don't have interference and impedance of the two participants. And today, since we're going to be talking about dual impedance, what we will be doing is taking thoracic impedance like we're typically used to, but also introducing impedance on the calf in order to look at the pulse arrival time as it leaves the aorta and makes it to the periphery. So that being said, whether you knew it or not, you may already have all of the pieces of equipment that you need. So I wanted to highlight, especially since this has been a more medically leading measure, why psychologists should care about pulse wave velocity. So one of the areas where pulse wave velocity has generated a lot of interest is in stress research. We know that chronic psychological stress doesn't just influence the autonomic nervous system, it also affects the vasculature over time. So as repeated stress exposure accumulates, we begin to see changes in arterial stiffness that can ultimately be reflected in pulse wave velocity. This makes pulse wave velocity an interesting complement to our more traditional autonomic measures because it captures another component of how the cardiovascular system adapts to chronic stress. Pulse wave velocity has also become one of the most widely accepted non-invasive markers of arterial stiffness, and arterial stiffness itself is strongly associated with cardiovascular risk. In fact, pulse wave velocity is increasingly being recognized as an independent predictor of cardiovascular outcomes, which is why it's becoming such an important measure in cardiovascular medicine. And beyond cardiovascular health, there's growing evidence that vascular aging is closely tied to cognitive health as well. Researchers have linked increased arterial stiffness with declines in executive functioning, processing speed, and other measures of healthy cognitive aging. So while pulse wave velocity originated as more of a cardiovascular measure, we're now seeing it incorporated into much broader ranges of psychology and aging research. And maybe most importantly of all, for psychophysiologists, what I find especially exciting about pulse wave velocity is that it complements measures we're already collecting. If you are using our mobiles or BioNexes to collect ECG and impedance, pulse wave provides an additional window into vascular function that can be integrated into the same protocol. So rather than looking only at cardiac control, we now begin to incorporate information about the vascular system as well. As this non-invasive measure makes its way into more behavioral research, acute changes in pulse wave velocity may be better understood. So very important as far as the research opportunities that exist with this relatively new non-invasive measure. So now that we've given a little bit of a background about pulse wave velocity, I want to break down what exactly this is, starting with the anatomy. So when we are talking about pulse wave velocity, we need to first start with the heart. This is where every signal is going to be generated from, and our measurements at the periphery will follow. So electrical activation of the heart triggers ventricular contraction. And following ventricular contraction, this ejects blood into the aorta. This is incredibly important because we're starting to see different signal chain effects. With electrical activation, we're seeing parasympathetic activity, and with ventricular contraction and impedance, we're starting to introduce mechanical properties as well. The aorta is especially great at its job as far as being able to eject this blood and create a pressure waves that travels throughout the arterial system. The aorta itself has a relatively thin diameter relative to its size. And so because of that, it acts as a very great pressure gauge. It's able to recoil and save energy in order to either speed up or slow down the blood as that is ejected from the heart. So outside of just the anatomy, I want to talk about what determines how fast pulse wave velocity travels. And this is really broken down into both structural and functional properties. So when we're thinking about structural properties, these are going to be changes that will take effect over time. So one thing to note is that, again, we need to ground it in the physiology. We have our arterial wall, which is composed of 3 different layers, and largely we see elastin and collagen within these living tissues. And what we find is that with aging, we see vascular remodeling due to aging and also exposure to risk factors. And so as we see that maybe our elastin and collagen with age is starting to break down, this will affect the speed of the pulse wave, meaning that it likely will be traveling faster as we're not able to dampen that signal. When it comes to functional properties, this is going to be things like in the moment changes that can also affect pulse wave velocity. So our arteries are living tissues, which are embedded with a bunch of nerves. And because of this, whenever we see sympathetic nervous system activation, we will also see that within the arteries. And so given this, when we see sympathetic nervous system activation, this will likely be increasing our pulse, our speed at which the pulse arrives at the periphery. Another thing to take into account is that in the artery, we have vascular smooth muscle. And if this muscle is relaxed, we're able to dampen the effect of the pulse wave. But if we find that this vascular smooth muscle is quite constricted, this will then again allow for that pulse wave to travel faster throughout the arteries. We're able to dampen it less. And maybe most importantly of all is that we need to take into account load-dependent influences. And largely when talking about pulse wave velocity, this is blood pressure. So when we are looking at changes in pulse wave velocity, as we see sympathetic activity start to increase, we may see that baroreceptor activity and blood pressure is also changing the speed of our pulse wave. So one thing that is recommended when collecting pulse wave velocity is that we also collect blood pressure so that we can control for and see the effects of just arterial stiffness. Okay, so one other thing to know, we need to recognize that not all arteries are built the same. So near the heart, the aorta specifically, arteries are highly elastic and they're designed to expand with each heartbeat, storing some of that energy before recoiling. And as we move further away from the heart, our arteries eventually become more muscular. The balance between elastin, collagen, and vascular smooth muscle changes depends on where we are at in circulation. So these structural differences influence how the pulse wave travels, which is one reason pulse wave velocity varies depending on where it's measured. So since we've talked about pulse wave a bit, I wanted to use this graphic to show exactly what this looks like in our signal chain. So here, what you're going to see is the aortic blood flow and the pulse wave as it leaves the aorta and is uptook again. And with this, we're going to see data from someone who is 18 years old, 30 years old, and 60 years old. So what we can see here, again, as an effect of aging, is how fast this wave is going. So starting with our 18-year-old, we see that our pulse wave is traveling relatively slow. We get it to go across the body and it's reuptook. Slower, able to control, we have more vascular, we have less stiffness in the arteries at this age. As we then get to 30 years old, you can see that this pulse wave as it leaves the aorta is starting to get faster and faster. And the other thing to note here too is that as we're starting to look at aging effects, our pressure wave is also going to change over time as well. So as we then move into our 60-year-olds, we see that this is traveling significantly faster, where we have a much faster speed. So that being said, another thing to note here as well is if you are interested in learning more about these aortic pressure changes over time, I'd also recommend looking at this Mitchell et al. Publication, which will speak to these aging effects of the pressure wave. So now that we've seen how the pressure wave travels, I want to talk about some of these traditional approaches to measuring pulse wave velocity, since again, these were much more medically leaning. So when looking at pulse wave velocity, this has been equipment that's considerably more invasive. It requires specialized training. It's more expensive. And so in order to look at pulse wave, people have used Doppler ultrasounds. Most commonly is using tonometry, which essentially is the gold standard for looking at carotid femoral pulse wave velocity, where we're able to see when blood is ejected out of the aorta and when it arrives at that femoral site. And then maybe most invasive or most expensive, definitely, is the MRI. And with all of these different data collection methods, you're able to get very precise pulse wave measurements, but again, at this cost of money, expenses, invasiveness. And so when we've been looking at pulse wave in the past, the other limiting factor here is that these are often brief vascular assessments rather than continuous psychophysiological recordings. So we're only getting a brief insight into what that person's pulse wave looks like. So in order to combat this and for us to be able to look at pulse wave velocity in a way that's much less invasive and much more easily able to be implemented within labs, we are going to be using dual impedance cardiography, which is a much more lab-friendly alternative. So what you will see here is that you will, when using dual impedance, again, if you're familiar with collecting impedance on the torso, this is just putting impedance on a different portion of the body to see that arrival of the pulse wave. So what we will see here is that we have simultaneous ECG, thoracic, and calf impedance cortex. And this will use the same impedance methodology that you already know, where we are treating our R peak essentially as our timing anchor that synchronizes both impedance waveforms. So the interesting thing about pulse wave velocity via dual impedance is that this directly measures pulse transit time from the ventricular ejection to the pulse arrival. So if you're used to collecting impedance, typically we are using our Q point as far as electrical activation of where the aorta opens. We then will look at the distance between Q and B to see when the aorta actually opened and its mechanical properties. And so what we're then doing is attaching impedance to the leg, which we then see this even more delayed effect of getting an impedance waveform of when this pulse is arriving. So the thing that we're going to take into account when talking about pulse wave velocity is really twofold. We're going to be talking about the distance in which this pulse has traveled and also the timing delay as far as when these measures appear following, again, everything following the heartbeat. One other thing to note here is that with this non-invasive measure coming out of Pete and Mark's group, they've also validated dual ICG against the gold standard carotid femoral artery. And what we find is that dual ICG pulse wave is highly correlated with gold standards of pulse wave. So that being said, when we are looking at estimates of this non-invasive measure, it's incredibly helpful to know that this is within, that we also have outcome factors that are correlated as well, as far as dual impedance being associated with cardiovascular risk and also things like mortality rate as well. So again, to really kind of hammer this point home, that this is just going to be looking at impedance from a different perspective. And what we have is the same technique, but just at different recording sites. So on the left that you see here, this is your typical chest impedance of our Z0 and our DZDT signal. If you've ever done training with me, you know that I like to say our chest impedance is our lumpy triangles that are riding this wave of respiration that we can see. And then once this has been mathematically derived of DZDT, we find that we have these much tighter triangles of a point and a fall off for every time that blood is ejected. So when we are looking at our typical impedance waveforms and we compare that to those of the calf, these are very, very similar. We see the same overall shape as far as our Z0 waveform. Of course, with the calf, we're not seeing as obvious respiration influence. And additionally, with the DZDT waveform, we see that we still get this precise peak of when the pulse arrives, but inherently this is a slightly messier signal because, again, we are looking at impedance on the calf. This is a large muscle group, so we're also fighting all of that EMG noise as well. So generally, the waveforms will look quite similar, but just always with this caveat that calf impedance is going to be slightly messier. So with this, the 2 points that we care about the most are going to be the B notch. So similar to what you're used to with your thoracic impedance. B is where the opening of the left aorta occurs. And when we are using the B notch in our calf DZDT, this is where we can either use the foot or the peak to speak to the peripheral pulse arrival. So now that we've talked a little bit about the methodology of how we would collect pulse wave velocity, what type of physiological groundings it has, I want to talk about how to actually make this calculation from dual impedance. So the number one thing to note here is that pulse wave velocity has there's a lot of things that have to go right for us in order to be able to calculate pulse wave velocity. We need clean ECG data, chest DZVT data, and calf DZVT data. And with this, if even one of these is missing, this will inherently affect our ability to calculate pulse wave velocity downstream. So as we mentioned, pulse wave velocity is really looking at a measure of distance and time of this pulse wave. So the first component that we need to talk about is pulse transit time, which represents the time component of pulse wave velocity. And pulse transit time is the time required for that arterial pulse to arrive at the periphery. So what we see here, similar to what we talked about in our PPG webinar earlier this year, is that we're going to overlay all of these waveforms so that we can see based on either Q as the opening of the aorta, or people can also ground this at R. It doesn't matter which you're choosing. We are really just looking for a precise timing measurement in order to go through and make sure that these calculations are reliable. So that being said, in order to get this arterial pulse transit time of when the aorta opens and when we see this at the calf, we're gonna take a few different measurements in order to get this arterial time. We're going to use our traditional PEP, which is looking from Q to B in order to see where that aorta opens. And then we're also going to take the calf pulse transit time, where again, either from Q or R, looking at the foot of where this arrives, or also the peak of where this arrives. You have multiple options of what points you want to fix to. The biggest point that I would make is, especially if you are introducing pulse wave for the very first time and you're doing like a replication and extension of a study that previously used it, look at their analyses, see what points they used. If you want to draw comparisons between those studies, let's make sure that we're replicating those steps as well. Okay, so in addition, I want to talk a little bit about what pulse transit time tells us. So here, especially going backwards, where we saw that we are looking at PEP and calf PTT, we are going to take calf PTT minus PEP in order to get this arterial PTT time. And so pulse transit time reflects properties of the arterial system and how effectively the pulse wave travels through the vasculature. So generally what we're seeing here is that if we have a shorter pulse transit time, meaning that these measures are getting closer together to one another, we are going to see a faster pulse wave velocity. And in the opposite sense, if we have longer PTTs, we'll see these measures start to space themselves out from one another. And this will then result in a slower pulse wave. So because of this relationship, again, PTT has been used as an indicator of arterial stiffness and also vascular control. So since we talked about the time component of PTT, how long it takes to get from one point to another, we also need to talk about the distance that is taken into account for calculating pulse wave. So when we are taking the distance, we are starting again from this aorta all the way down to the calf. So we are going to calculate pulse wave velocity by looking at the path length in meters and dividing that by the arterial PTT. So distance divided by time, giving us how many meters per second in which this pulse wave velocity travels. So the nice thing about the standardization of this calculation is it allows comparisons across individuals and also recording locations. Today we're talking about dual impedance on the calf, but same goes for PTT like we talked about with PPG. You can collect this from different locations, and depending on the distance will also then affect the pulse wave relative to that site. So one other thing that we need to take into account as we are starting to talk about pulse wave velocity is also some of the factors that influence it. So pulse wave is derived from precise measurements of both distance across the body and of pulse transit time. So again, in order for us to get reliable and valid calculations of pulse wave, we need to ensure that we have clean ECG, clean DZBT for both our chest and calf. And again, if even just one of these is not good, this will have a downstream effect on if we can work or calculate pulse wave. So the other thing to note here too is that we are going to need precise signal synchronization. Again, that R peak is our moneymaker. It is the most reliable point in order for us to make these reliable timing differences. So we need to make sure that depending on how we're scoring, a fixed to Q or a fixed to R, that we keep this consistent. And then lastly, one thing to note here is that we did talk about how dual impedance has been validated against the gold standard carotid femoral pulse wave. The one thing that we need to take into account is that this is a slight overestimate of pulse wave velocity as opposed to the gold standard. And the reason for this is just because we have longer distances that we are taking this measurement from. We are going all the way down to the calf, and again, using our PEP to speak to these timing differences versus our much more medically leaning measures are going to get direct measurements at the carotid femoral, whereas we're making this, whereas we're using PTT to leverage this. Again, we also need to take into account acute influences. So much of what we talked about earlier, sympathetic activity, blood pressure, vascular tone, these are all going to have effects on pulse wave velocity in the moment. Another thing as well, just highlighting what you probably already know from collecting impedance data, is that impedance on the leg is also going to be associated with postural shifts. So if we see postural shifts, we'll see changes in this data or waveform. And then maybe most importantly of all, there's a lot of control factors that we need to take into account when collecting pulse wave velocity. The largest are probably age, smoking status, and cardiovascular health. So again, as we discussed, as we begin aging, our pulse wave velocity is going to start increasing over time, meaning that our pulse and our aorta and arterial stiffness is not allowing us to dampen that waveform. So we will need to control for age, and there's also, as you can see here, kind of the normed intervals of what we would expect in certain age ranges. But again, this can also be affected by the person's overall cardiovascular health and other individual variables like smoking status as well. So now that we've talked about what pulse wave velocity is, I want to talk about how you can measure it within the MindWare ecosystem, again, likely with equipment you already have. So as far as the hardware requirements, since we are collecting dual impedance, we will either need two mobiles that are frequency offset from one another, or a BioNex that contains multiple impedance cardiograph 2 slots. So if you have a BioNex that has multiple slots, when we are collecting impedance, since our red electrodes on the back essentially send the constant current through the front of the chest, we need to make sure that these constant currents are offset from one another while we're collecting on one person so that we do not get interference. This is likely already configured for you with your BioNex, but with your mobiles, this may be different. If you work with diodes, your mobiles are likely already frequency offset for impedance. But say, for example, you're someone who has multiple mobiles within your lab, but you only collect data on individuals, it may be that your frequencies are not offset from one another. This is important because if our frequencies are not offset from one another, what we're going to see is as we're injecting two constant currents of the same current at different sites on the body, we're going to get a lot of interference as far as in our Xena and DZDT signals. So that being said, if you think you maybe fall into this category where you're interested in collecting pulse wave velocity, but you're not certain that your mobiles are offset from one another, you could always send them, you could always contact us at support, and from there we can arrange for a shipment of your mobiles back into our back into our office, where we will then offset the frequencies for you and send them back. This is like a very relative quick turnaround. So that being said, you could get back to it very quickly too. Okay, so I want to talk about electrode placement because now we are going to be leveraging the same principles of impedance, but with a few extra caveats. And again, since we're introducing this measure for the first time, I wanted to speak to how we would be seeing this in the waveform. So very first thing, we already know that we are going to collect standard ECG and impedance from the thoracic, and we will take this measurement of our chest distance starting from the bottom of this top positive electrode to the top of this bottom electrode. This is essentially determining the height in which we are treating the chest like a cylinder to determine how much blood can visibly move about the chest cavity. And so with that, when we are collecting cath impedance, we are going to be following the same principles that you are known and familiar with for electrode placement, but just in a slightly different location. So here, what we have, and similarly to what you're used to for thoracic impedance, I am going to first start by placing the red electrodes on the left outer side of the calf. So when we are placing electrodes, this will also follow our standard of our positive electrodes up top and negatives on the bottom. And with this, we are going to place the negative electrode kind of just right above that ankle bone on the far left-hand side. And then for the positive electrode on the calf, this is going to, again, be on the left-hand side, right kind of where when you start bending your knee, you can see the little knee bones start to pop out here as well. And these are kind of your standard locations for those red electrodes sending the constant currents. We then are going to use our white electrodes on the other side of the calf. And these are going to, again, look at when that pulse wave arrives at the periphery. So rather than starting with the white electrodes and then placing the red electrodes later, like we do for chest impedance, this is opposite. We'll start with those red electrodes, and after these red electrodes are placed, you're going to want to take a 4-centimeter measurement and use that to determine where your positive electrode is here, slightly lower than your red. And same with the negative electrode. You're going to want to go 4 centimeters up on the other side of the calf in order to give enough clearance for these electrodes sending the constant current to be picked up on this side. So again, these electrode placements are maybe in a new location, but follow similar principles to what you're used to. The biggest thing that I need to harp on here in order to make pulse wave velocity calculations is really talking about the additional measurements that we need to make. So since we need to determine path distance, we need to look at the overall clavicle deltoid height. So what you're going to ask participants to do is take off their shoes, and from floor to standing, we are going to measure the distance of our clavicle deltoid, because this should put us right in line with our aorta of talking about this distance. So we're going to take this as our first distance, and then we're also going to take our calf height distance of from this time shoe off, seated, but measuring from floor to the midpoint of the calf between our two white electrodes, in order to then, again, take this clavicle deltoid height minus this calf height in order to get the total path distance. The biggest thing to note here is that these measurements are incredibly important for us to get precise. Since path distance is its own variable in the pulse wave velocity calculation, if we have if we have variability in how research assistants are measuring these distances, this is going to be the easiest way to inject incorrect variability into our pulse wave calculations. So that being said, as we start to do these distance measurements, we want to be really precise, make sure everyone is very well trained on it, and also take into account that with these different body frames, we really need to get this as a straight line in terms of the anatomical path, regardless of body frame. Okay, so now that we've put electrodes on, you would go back into your standard biolab acquisition protocol, but this time just enabling new channels as far as the Z0 and DZDT of your CAF data. Maybe the most important thing to note is that oftentimes when recording in BioLab, I like to leave filters off so that I can see my raw data. And then from there, post hoc, I can always add any filters as needed. But with the CAF, Z0 and DZDT, since we are, again, looking at the impedance in that large muscle group, we have a waveform that has more noise to it. So in order to have a good visualization of the data at the time of recording, I like to apply these Z0 and DZDT filters, which are suggested in the Scudder 2021 dual impedance article as well. So after we have collected all of our data in BioLab, our analysis pipeline is going to begin. And again, this is where we're going to follow step by step by step in order to eventually get to our pulse wave calculation. So a few things that are going to be different for you in your typical analysis pipeline that I wanted to highlight the importance of as far as these extra steps if you're interested in collecting pulse wave. So starting from our ECG, since we had applied BioLab filters to our Z0 of our CAF and DZDT, these filters will not automatically be carried over into your analysis applications. Instead, you need to go to File, BioLab Filters, and turn these on at the HRV stage. So the reason why we must turn these on at the HRV stage is because if you go through and score your HRV data and use that EDH2 file in order to leverage your HRV edits in your both thoracic and CAF impedance, once we start editing, that locks in all of our settings. So even though we aren't touching impedance yet, we need to enable these filters at this stage so that they get carried over in our edit files as well. And then after we have scored our ECG as typical, we would go in and score our thoracic DZDT as typical as well. So again, this is where we would leverage our EDH2 edits, where we're then locking in all of the edits we've made for correcting things like midbeats. And we're then able to ignore all those estimated beats, but look at the Z0 of the chest and of the chest as well as its DZDT for scoring. And again, if you're familiar with impedance, this is just going to be following your standard impedance scoring as you typically know based on your ensemble averages. With that, as we get into CAF DZDT, this again speaks to your analysis pipeline. So you edit all of your HRV data first, then you edit all of your thoracic DZDT, and then we come in and look at our CAF DZDT. So the same thing applied here. We will leverage that EDH2 file for our ECG edits, but this time we will be mapping the CAF, Z0, and DZDT here in our impedance channel mapping. So given this, the one thing to note is that when we're working with thoracic impedance, we're going to be using all of our standard settings as typical. But once we start to get into our B-point calculation method, as far as determining when that pulse arrives, we are going to make a setting change. We're instead going to use max slope with a block of 30, which is going to give us kind of the foot of where that pulse is arriving, where we see the maximum slope change of that pulse arrival. So that being said, this is one place that you would make a setting change for that calf point. And again, if you were interested in looking at affixing your PTT interval to R, you could leave this Q point calculation setting, but just change the constant value to 0 so that we are affixing that at R consistently. Okay. So once we get into calf DZDT, we need to talk about some of the editing rules. And generally, this is going to follow the same editing rules that you're used to with thoracic impedance. In this case, unlike HRV, we do not care about continuity. We care about good cycles of ECG with good cycles of calf DZDT. And so generally, when we're editing, we're going to go for a less is more approach. The beauty of working with calf DZDT and impedance editing is that our ensemble average is the pictorial average of every cycle that we are including in that given segment. And so because of this, we're going to delete the most obvious bits of noise first, because our ensemble average, and the beauty of an average is that it rejects random noise. So as we remove these outliers, we will have an ensemble average that is better defined. So same thing here, we're going to be taking a phasic editing approach. We will look at our ensemble average, determine how much editing we think needs to be done. We'll start with the obvious bits of noise, and then we will check our ensemble average after this first round of editing to see if our waveform has improved. If this is the case where we get done with our first round of editing, we still think that, maybe our peak or our B could be better defined, what we will do is wash, rinse, and repeat this process informed by the ensemble average of, depending on what piece of the waveform looks like it needs more help, we'll determine what edits we make. So similarly, when it comes to calf impedance, we are going to have the same type of artifacts that we're used to seeing with thoracic, just displayed slightly differently. So similarly, electrode placement is going to be key, and it's always going to be important in biolab to check your preview screen to make sure that we have good impedance data for both Z0 and DZDT. If we have data that isn't well defined from the start of acquisition for our Z0s, where we're not getting those nice kind of lumpy triangles over and over again, we're going to see that directly affected as we detrend into DZDT. We're not getting as much definition around our peak of our pulse arrival, and this is going to make scoring considerably more difficult. So depending on how much lack of definition there is, this could be a file that you consider excluding from final analysis. And then additionally, the common DZDT artifacts are going to be the same as thoracic. We are going to go about and delete the most obvious bits of noise first. And so this is likely going to be due to things like movement, or when movement has become so extreme, we see effects of railing or square waves in our data where we're going out of range. We may see that our DZDTs start to get a little shelfy or rounded versus being well-defined, and we don't want to use those. So we are going to take into account all of these common artifacts, and as we see them, we will delete them from our segment if we find that it's affecting our ensemble average too much. Okay. And as far as artifact correction, this will also mirror the rules that you're used to following with thoracic impedance. So similarly, since HRV has the most rules around segmentation times and how much data is needed in order to calculate RSA, what we will do is we are going to match our segment lengths in our thoracic and calf DZDT data to match those of our segment lengths in HRV. These again need to be at least 30 to 60 seconds. We typically recommend editing in 60-second segments just for ease of data retention. But same thing here. We are going to carry that segmentation length across all of our measures for ease of comparison. And when it comes to our HRV data, again, making sure that we have clean data each phase of the pipeline. We need to make sure that we are only using segments that have less than 10% of midbeats. Again, if you're starting with your HRV editing first, which you will be, this will be controlled for in your EDH2 edit files, meaning if you have already ruled out a participant from HRV, that has a downstream effect into your other impedance data. And lastly, maybe the most specific to impedance is with impedance data, we are used to seeing more artifacts. It's more sensitive to electrode placement, it's more sensitive to movement. And so we may see that there are big spurts of movement over time. We're again going to take out those big pieces of noise for our good, clean cycles to shine through. And overall, we can work with pretty messy data, but in a given segment, we want to make sure that we're retaining at least 50 to 60% of the overall data in order to retain that segment. So we may have some movement and scatter different pockets, but as long as we overall get at least 30 seconds worth of data, we should be good. Okay. And then lastly, most of the time you hear me talking about our analysis programs, but today I wanted to take it a step further when talking about calculating pulse wave velocity, that we will do all of your scoring for your data in your analysis applications. But in order to calculate pulse wave velocity and pulse transit time, this will be done in your preferred stats program. So for today, we need to calculate the two components of pulse wave velocity. So the first is pulse transit time, which is, again, that CAF PTT starting from either Q or R, going to the B or C point of this thoracic, or of this CAF impedance, and then taking the PEP, Q to B or R to B, from that CAF PTT to speak to just the arterial pulse transit time. How long from the opening of the aorta to the arrival of the periphery. So with this, you will take your output data from MindWare and you will make this calculation as a new variable in your program of interest. And then one step further, after we've calculated arterial PTT from CAF, PTT, and PEP, we will then start to look at our path length as well. So we are going to record these distances in centimeters, but when we are recording on pulse wave velocity, our path length is in meters. So this is again going to be the height of the carotid process from standing and that calf height, and then divided by PTT in order to talk through meters per second of how fast this blood is traveling. So although we just went through a lot of screenshots of what this data looks like, I'm going to give you a quick walkthrough in some of our data of what this would look like in the impedance application and what this would look like in SPSS, my preferred stats program. So I am going to go ahead and open up my impedance data, and a special thanks to Mark and Pete once again, who provided these really, really gorgeous data examples. So going a step backwards, I am going to go to my channel mapping screen. And for our purposes today, I'm not loading in an EDH2 file. I'm going to start with our raw data for ECG. And jumping right into calf editing, I am instead going to map Z0 for the calf and DZDT for the calf as opposed to the chest measurements. So when doing so, I have those channels loaded, and I will also go through and make an adjustment to my B point calculation. So again, all standards will be all settings will be standard to what you see in our default. You again have the ability to affix our Q point to R depending on your PTT interval of interest. But largely, we're going to come down to this B point calculation method and change it to max slope with a block of 30. So the other component that I want to highlight here is right now, I do not have any biolab filters turned on. So when I go into analyze my data, what we see up top is that we do have a bit of fuzziness to our waveform as far as when we're looking at that foot or arrival time. This is where we're getting the most noise coming in from, again, that EMG. But what we're seeing here is the effect of without biolab filters. And even though this is quite noisy, when we look at the ensemble average, we still have very clearly defined foots and peaks of our waveform relative to the ensemble average rejecting that noise. But one thing I want to highlight is showing you the difference of what this looks like when we do have biolab filters enabled, which makes a big, big difference. So although we still have some fuzziness, this definitely looks better than what we were seeing in terms of ease of visibility. We can see that our ensemble average is a bit less shaky. So again, this is just really highlighting the importance of what it looks like in terms of carrying over biolab filters, making sure that we do that at HRV to have it in a downstream effect in our CAF editing. So similar to what you're used to, we have our cycles of ECG and this time CAF DZDT instead of thoracic. And what you'll see here is that your ensemble average will follow the same principles. The only idea here is that you're going to see a much larger gap between where we would typically be used to seeing the thoracic impedance. This is totally normal. Again, we're looking at a measurement on the calf. It has to travel the distance of the artery, so its timing is delayed. That being said, you are going to notice that your PEP values, which is really your Q to B of arterial PTT, are going to be significantly higher. So this is totally normal. And again, calf PTT that we will subtract from PEP. The one thing to note about our program is that since you are using the impedance program for calf impedance, this will by default say PEP, but again, it's still just that same measurement, Q to B of arterial PTT. Another thing to note here too is that you will be seeing higher Z0 values in all of your calf waveforms. So as you look at the thoracic to calf, you'll see that this increases as well, but this is totally normal and expected based on the area that we're working with. So as we look at this data, I wanted to just first give an example of what really, really amazing data looks like. Clean, barely anything that needs to be touched or edited at all, as all of these cycles look consistent across this 5-minute epic of a paced breathing task. So the important thing to note here is that when we're looking at clean data, again, we can still see that there's a little bit of noise within the signal. That all gets washed by our ensemble average, making sure that, again, we have clear distinctions of our B and Z. So that being said, I am going to open up a different data file, one that doesn't look as pretty, still very, very pretty, but one that requires a bit more editing. So same thing here, mapping our ECG and our CAF DZDT, ensuring that my biolab filters are on and carried over. And from here, I see that, and this particular file, as we apply biolab filters, this looks even a bit cleaner than what we were seeing. But we do have some effects of movement here. And although this is very little, like here and here, we still have like I said, a really gorgeous ensemble average. Good definition around our peak and good definition around our foot as far as where this pulse arrives. So as we look across this data, we see that it is relatively clean, but as we start to get into segment 4 and to segment 5, which has a bit more noise, our ensemble average is looking a little different. It has less definition to it, and its waveform looks slightly different. Before, we were looking at PEPs of like 120, or excuse me, 260, 252, 255. And as we make our way into 4 and 5, our PEP is still within a relative range of 258 and 261. but we see a lot more shakiness here. So again, less is more. And we are going to take out the most obvious bits of noise. So our ensemble average looks pretty good, but we do see that there is all this movement at the end of this file, likely making these good waveforms just look very small relative to the movement. So that being said, we're going to go into our edit Rs, and then we are going to zoom in. I am going to cheat a little bit. Typically, this is where I would say examine all of your peaks, but I'm going to skip right to this back section of movement. And so what we see here is that prior to the movement, when I zoom in by clicking my magnifying glass and zooming in on my x-axis by clicking and dropping, I see that I had some pretty good signals. They look a little small right here just because this is relative to this big section of movement. But if I zoom in on my y-axis, we can see that there actually was pretty good definition to these feet and peaks. So when zooming back out, and again, functioning and looking at just this back half of movement, we can start to see that, yes, we had good and clearly defined peaks, but as we start to get into these sections of movement, things are too pushed around. It's not easy for us to tell where the clear foot and trough is of this calf DZDT waveform. And so for any cycle that we do not want to include in our ensemble average, we will delete the blue peak from the top of the ECG cycle corresponding to the DZDT cycle. So that being said, we only want good cycles of ECG and calf DZDT together. So in all instances of movement, we would come through and delete these cycles. And before closing out and hitting the X button, I'm going to pull my ensemble editor down, or excuse me, my edit Rs down so that I can see my ensemble average before I had made any edits. We were at a PEP or calf PTT value of 261. And when I close out here, we will see our ensemble average update as well as our PEP values. So when I hit close, we see that this starts to change our ensemble average. We saw that what was maybe a little shakier beforehand had flattened out with the removal of that data. And we also got a slight adjustment in our PEP values, becoming shorter than what they were made to look like with movement obscured. So we would follow these same principles with less is more with impedance of really making sure that we're taking out the obvious bits of noise, but after everything has been cleaned out, that we're able to write out all of our data to our output files to continue this pulse wave velocity calculation. So now that we did just a very brief editing example, I am going to open up SPSS. And if you're familiar with our output files, after creating, after scoring your data and writing out your output files, I have taken those output files and I've just grabbed out the information for this last double peak file that we were looking at of the PEP values that came from the Q to B distance across all 5 segments. I also then grabbed the calf PTT, so that Q to B foot that I used in this measurement here, across, again, all 5 segments. And then from there, I created the arterial pulse transit time variable by going to transform compute variable. And again, arterial PTT is calf PTT minus PEP. So right now, these are reported in milliseconds, but since we are going to be looking at meters per second for arterial PTT, I've just converted this into seconds. Additionally, we are also going to need all of those height measurements. So one thing to note, within our programs, there isn't going to be a great spot for you to input this information. So as far as your study checklists, or if you're filling out like Qualtrics forms for every study run, you are going to want to store that, again, standing shoe off height from floor to the AC joint of that aorta distance. And then same thing, this time from sitting, shoot off the calf height of the midpoint between our two white calf impedance electrodes. So with these, we are going to then create the path distance, which is going to take the floor to that clavicle deltoid height and subtract it from the calf height, which again, I created this double peak path distance variable from going into transform and compute and creating that variable. After we've created the path distance, you'll see here that I have fluctuations in my PEP and calf PTTT by segment, but for ease of comparison, I just carried through the heights consistently for all of these segments for the calf and the AC joint. So once our path distance is calculated, I also want to call attention to the fact that these were measured in centimeters, but we will also be making another conversion. And this time, this is going to be converting into meters. So finally, going off of, now that we have created the path and we have gotten the timing principles, we are going to calculate pulse wave velocity. So what I ended up doing was I ended up going to transform compute variable, and I created a variable for pulse wave velocity in which I took the path distance and divided it by the arterial PTT. And when doing so, this gave me pulse wave velocity at each of the 5 different segments. So depending on your task or protocols, you could look at this on a segment by segment level and then average across all segments to get a pulse wave velocity value at a epic or task level, or depending on if you're just doing something like a seated baseline or a paced breathing task, you could consider looking at one pulse wave velocity measurement across the average of your PTT of all 5 segments. So that being said, today was a bit of a crash course on impedance cardiography in the calf in order to look at dual impedance. I hope that you guys enjoyed this, especially because this is a measure that has maybe been sitting around in your lab that you didn't know that you could collect. But that being said, this is something that you could start implementing very fast into your work now. So getting back into the PowerPoint for just one second. I wanted to open things up for Q&A before we wrap up our last closing thoughts. So give me just one second. I am going to open up our Q&A doc. I saw that some questions have been coming through. So I'm first going to start with the customer question that came in. I may have missed it, but can traditional impedance derive ANS metrics and pulse wave velocity be collected simultaneously, or is it one or the other? Great question. I am actually going to jump back out for a second to slide 25 and give me just one sec to get there. Okay. So when we are measuring PTT. Pulse wave velocity. We can do this with two different systems. So we could use this through our mobile systems where we're attaching one mobile to the chest and one to the calf. And the beauty about pulse wave velocity is that it already integrates into your existing studies. So we will continue to collect simultaneous ECG and thoracic impedance at the same time that we're collecting this calf impedance. So really, really beneficial for all the metrics you're already planning on reporting on. You then get this additional one in tandem with just the addition of 4 new electrodes and 2 additional measurements. Great, great, great question. Jumping into it, I am going to field some of the other questions that we've gotten from the audience. So one question that we didn't touch on today, but is very important, especially since we do have a lot of researchers who do child research versus adults. I talked about everything today in the context of pulse wave velocity for adults, getting at that 18 and up age range. That being said, there has been pulse wave velocity research done to look at the comparison of the meters per second of arterial stiffness in children versus adults. So this paper actually comes out of another one of our users, Lee Stoner, who looked at pulse wave velocity using the typical tonometry measures. And with that, with aging and with development, we need our arteries to get thicker over time and stiffen in development. But at a certain point in adulthood, the stiffening then becomes adverse. So when we're looking at kids, typically we're seeing that pulse wave velocity changes of 0.12 meters per second per year, versus in adults, we're seeing that we're having a relative pulse wave change between 0.2 and 0.7 meters per second for every 5 years. So as you can see, in development, we need to rapidly increase our arterial stiffness, but then with age, this will then more gradually happen over time. And so again, for our child researchers, I know I talked earlier that this is a relatively untapped field as far as looking at the non-invasive measure of dual impedance. So not only does it have a lot of interesting opportunities for psychophysiologists to look at acute behavioral changes, there's also still a lot of work that needs to be done in the child literature too. So plenty of room for publications for all. Okay. The next questions I have are about some hardware requirements. So, one thing I want to talk about, and one question that came in is, what frequencies are the mobiles often tuned to for pulse wave velocity? Is this the same as the BioNex? So, with the mobiles and with the BioNex, we talked about how our red electrodes send a constant current through the front of the chest or through the side of the calf that needs to then be used as a constant current so that we can assess the resistance change in these sensing white electrodes. So that being said, when we are doing frequency offsets, these will be the same for both our mobiles and our BioNexes. It does not matter by device per se. The only thing that we need to do is adjust these frequencies so that we do not get interference. Oftentimes, our mobiles are set individually to a chest measurement of 100 kilohertz for that constant current that comes through. And graphically here, I've showed a low frequency and a high frequency to display the visual differences, but realistically, we're only offsetting these ever so slightly. So we would set the chest to the traditional 100, and we might do the calf to 101. All that matters is that these frequencies are not the same, so they do not interfere with one another. If we were doing, say, dyads with pulse wave velocity, and we were looking at parent-child relationships, and we were concerned that there may be touching that's going to occur in the study from maybe the parent consoling the child, One thing that we'd also need to take into consideration here is if that's the case, or if that fits your study protocol or your population, let us know, because if we're concerned that there is touching involved, we'll make this frequency offset even larger just so we have less interference. Okay. So additionally, we have one other question about the frequencies. So, one question is coming from someone that says, I have multiple mobiles. How can I tell if their frequencies are offset from one another as is? This is a great question, especially for those of you who do individual research. You don't typically work with dyads. If you have multiple mobiles, and especially if you've purchased them at different times, like one a few years ago, one more recently, and you only typically use them on individuals, it's very likely that your mobiles are not offset from frequency from one another. And to be honest, you wouldn't know that because until you started to use them together, you wouldn't be observing any interference. So that being said, if you are concerned or you want to test this to see if we do have frequency offsets, what I would recommend is following the steps of today and going through and essentially putting the mobile on the chest, putting the mobile on the calf, and then seeing in BioLab in your preview screen if we have clear Z0 and DZDT data. This interference will be very obvious to you. Very, very, very obvious. It's thick, it's big, you can't see really anything underneath the waveform. So that being said, I would recommend doing a little test run on yourself to see if there's no interference observed. And if there is interference observed, that you're interested in having these frequencies offset, like I said, please contact us at support@mindware.tech. We will have one of our support case representatives arrange a shipment of your mobiles back into our office. And for a small fee of about $100 plus shipping, we can get those frequencies offset from one another and back to you within a matter of a couple of days. Okay. Okay. One last question, just a very important one for today. I want to, someone asked, when reporting on pulse wave velocity, do I need to control for blood pressure effects? So this is the last question that I'll answer today, but this is a very good one because this is really important into the opportunities for research. So, if you have blood pressure in your lab, we would recommend collecting it in tandem with dual impedance cardiography. The reason for this is, again, thinking of those functional properties that blood pressure can speed up pulse wave relative to changes in baroreceptor activity. So given that, if we have blood pressure, we do want to control for it just so that we can, again, look at these acute effects of pulse wave velocity and arterial stiffness and vascular control versus effects of blood pressure. So that being said, give me just 1 second. I'm going to pull up some of our closing slides now that we've wrapped up questions for the day. But I just wanted to give us some reminders. So, as always, we are always here to support our research community. So I wanted to direct you to some of our resources and how to get in best contact with us. So, if you are interested in learning more about pulse wave velocity, if you want to add an additional mobile to collect it, you want to consider a new BioNex slot, chat with us. You can always reach out to us at sales@mindware.tech. Or if you already have mobiles, but you want to get their frequencies offset, feel free to hit us with an email for our support, and a support representative will chat with you. The important thing here is these questions extend well beyond pulse wave velocity. If you have anything going on in your lab, especially as you're getting prepped for fall semesters coming up, which is quicker than we maybe even imagine, feel free. We're happy to start answering some of those questions and get anything resolved or clarify questions for you. And lastly, I'd also recommend checking out our support site. On our support site, we have our knowledge base, which you're able to search in order to do a number of things. Look up how to configure different devices, how to scale your data, how to set configurations for different types of hardware. You name it, it's in our knowledge base, and you can search by keywords. So one thing I would note is check out that knowledge base. And of course, from our support site, this is where you can also download our software and create an open support cases to ask our scientific team further questions. Also on our support site is all of the training components. So very much my wheelhouse and where you may be interacting with me. Since pulse wave velocity is this measure hidden in plain sight, it's this measure that you may be already able to use with your existing software and hardware. This may be something you're interested in collecting for a next study, but if you want to take the principles that we learned today and slow them down a bit more, you could also reach out to our sales team to schedule self and one-on-one training opportunities, likely with myself, where we would take this whole process, slow it all down, do it with your lab of live acquisitions to look at signal quality, all the way to analysis of pulse wave velocity. So if you're interested in implementing this, you could also, again, reach out and book some training hours so that we can talk through this in more detail with your setup as well. And then, of course, our data analysis services. I always like to say after hearing these webinars, if you've heard it, you learn the principles of it, but you still don't have enough time to do it or enough manpower to do it within your lab, chat with us. We offer data analysis services where we work with you based on your study, your variables of interest, your analyses of interest. We go through and clean and analyze your data for you so that you can get it all back and then basically have a SPSS and CSV data set that you're ready to start running analyses of your clean physiology data from. So also another option if you're interested in outsourcing your pulse wave calculations too. And then, as always, from our support site, I also wanted to highlight our quarterly newsletter, which if you scroll to the bottom of our support site, you can subscribe to our mailing list. Our quarterly newsletter is, we don't blast you with emails. We only send announcements or things like when we're going to be releasing our next webinar, if there's any new updates in terms of software. And as we get closer to 2027 arriving, this will also be where we are starting to tease our new lines of hardware and software technology that will be coming out within the next year. So that being said, definitely keep an eye out. It's a great way to stay in touch with us, see what new is going on, and also join in for webinars and complimentary services like these. So I would like to thank everyone for attending today. I was very, very excited to give this talk on a measure that you may already be able to start playing around with right after this call. So of course, if you have any questions, please feel free to reach out to us. And as a reminder, I also wanted to include this last QR code. You will have a post-webinar survey after leaving this Zoom call. And in addition to that post-webinar survey, there's going to be a component asking about what type of webinar topics would you be interested in learning more about. As we are getting prepped for 2027 and thinking of webinar ideas for next year, it would be so insightful to hear from you guys of what topics you're interested in learning more about so that we can hopefully implement that in the following year as well. So feel free to scan that QR code to take you to your post-webinar survey. And other than that, I hope everyone has a good rest of their Thursday, that they've learned a lot about pulse wave, and that we'll be chatting with you soon. Bye-bye, all.